In this video, we are going to continue our lecture on electron configuration. Okay. Let's work on some exercise. Okay, let's look at this one. Number 10. Which electron configuration represents the violation of the Pauli's exclusion principle? So what is the Pauli's exclusion principle? It says there must be 2 electrons in each line and they will be in the opposite spin, opposite direction. Let's look. A, okay, up and down is good. Up and down is good. Over here, can I do it like this? No. What happens if I have 2 electrons? I need to do it, fill it up one by one first. So this one is a violation of Hund's rule. Okay. Violation of Hund's rule. Let's look at this one. Up, down, up, and that's all. Okay, I think this is good. Let's look at this. Up, down, up, up. You cannot have these 2 pointing up together. So this one is violation of the Pauli's exclusion principle. Okay, so let's look at another one over here. Up, down, up, down, up, up. This is fine. This one is okay. Nothing's wrong with it. You don't have to fill the center before you fill the side. Okay, let's look at this one. Up, you have to fill the lower level first. So if you have 5 electrons, what you can do is 1, 2, 3, 4, and 5. All right, let's look at another exercise. Let's look at number 13. Which electron configuration represents a violation of Hund's rule for an atom that is in its ground state? Okay, so let's look at each of them. This one, up, down, up, down, up, up. This one is good. Let's look at the other one. Up, down, up, down, up, up. So this part is not good. Why? You cannot fill this one before filling each of these with 1 first. Okay, so this one is violation of Hund's rule. Okay, let's look at this one. Up, down, up, down, up, up, up. This part cannot be 2 pointing up. This one should be pointing down. So this one is the violation of the Pauli's exclusion principle. Okay, and let's look at the other one. Up, down, up. That is fine. Let's look at this one. Okay, this one is up. So it's not in the ground state because I can clearly see that it did not fill the lowest level first. So if I have 5 electrons, it should be up, down, and up. Now, let's look at number 11. The ground state electron configuration of gallium, Ga is, okay, so gallium, it is Ga, it has 31 electrons. So how do we do this? The best will be go back to our favorite chart over here. Okay, so now I have my energy level over here and I have 31 electrons. Okay, so we are going to fill it up now. 31. Okay, let's count. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. Okay, so how do I write the electron configuration? It will be, starting from the bottom here, it will be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, and 3d10, and then 4p1. Okay, so this is the electron configuration for gallium. Okay, so if you look at this way, after the third level, principal energy level, so you add this. So all the way up here, now I have 18 electrons. So the first part, all the way up to 3p6. So this part, everything together, is the electron configuration for argon. So a short way of writing it will be just argon, and whatever left over here, we just copy that down. Okay, so this is the way to do it. There is a new term. It's called the valence electron. Valence electron. That means the outermost principal energy level electron. Which one is the outermost principal energy level? Is it the 4p over here? Yes, it's energy 4. And what about here? This one is 4s over here. So this one altogether is called the valence electron. I have 2 over here and 1 over here. So this one will have 3 valence electron. Once again, valence electron, we're looking at the highest the coefficient over here. So that is the principal energy level, is level 4 now. So I have 3 valence electron. Over here is the 3D, so the energy level over here is 3. So we will not count that as the valence electron. Now I'm going to show you a periodic table that shows all the electron configuration. If you look at over here, you see 1s1, 2s1. Okay, so all these group members in this family, I always can see S1, because they have the similar electron configuration. That means it ended up in a new principal energy level and it has 1 electrons in the s orbital or energy level. That's why they have the same or similar chemical properties. So from this periodic table, what you can see is the valence electron is the same. That means the outermost layer of electron. So over here, valence electron will be 1. Over here, it will be 1. Over here, Be, this one will be 2. So valence electron for over here, boron, group number 13, it will be 3. So principal energy level is number 2. So you see 2 electrons in the s orbital, s level, 1 in the p, so altogether there are 3 over here. So boron over here will have 3 valence electron. If you look at aluminum, Al, I'm talking about number 13 now, it will have 3 S2, 3p1, so 3 is the outermost layer, and there are 3 valence electrons. Let's look at the patterns over here. So over here, I have 4s1, 4s2, I'm looking at number 19 and 20 and on, potassium, calcium, 4s1, 4s2, and then 4s, 3d1, 3d2, 3d3, and on. It seems like there's a pattern, but you can also see exceptions. For example, over here, 3d3, the next one we should expect to have 4s2 and 3d4. But over here, chromium, this column is an exception column. So over here, chromium number 24, molybdenum number 42, tungsten number 74. You can see this column look a little bit different. And over here, the d orbital, over here, the d that's 5, d that is 5, d that is 4. So it's a little bit different. So those are the exceptions. And those are not the only two exceptions. Let's go ahead. So over here, we can see 4s245, 3d5, 4s2 3d6. So 5, 6, 7, 8. Over here in copper, number 29, copper, Cu. There's another exception over here. See over here, 4s2, but over here is 4s1. So this one, that is an exception. So we can see some columns that doesn't follow it. And you need to memorize those columns.